let's have a look at the last question in this paper. So this is a ladder question. Let's have a look. A rod AB has mass M and length 2A. So the rod has its end A on rough horizontal ground and its end B against a smooth vertical wall. So the ground is rough, so there'll be frictions on the ground, and then smooth vertical wall, so there'll be no frictions. And the rod makes an angle theta with the ground, which they already labeled here. And then the rod is at rest in Newton equilibrium. So if it's Newton equilibrium, then the friction is equal to mu r. And then part A state the direction of the frictional force act on the rod at point A. So let's just label all the forces first. So we have normal action at A, let's call it R. And then since it's Newton equilibrium, so the friction has to be mu times by R. And then the normal action is always perpendicular to the wall. So this should be to the left-hand side S. So then this one, the weight is equal to mg. And then, so part A, the direction of the frictional force has to be to the right because, so let me just write it first. So right as they are only two horizontal forces S and so two forces, and then the normal reaction at point B is acting to the left. So the friction has to act to the right to make the rod equilibrium. Because if you want it to be equilibrium, left has to be equal to right. So since the frictional force always act perpendicular to the wall, so always act to the left-hand side, then the frictional force has to be the right-hand side. Okay. And then the magnitude of the normal reaction of the wall on the rod at B is S, which we already labeled it here. In an initial model, the rod is modeled as being uniform. So uniform just means right in the middle, which we already labeled it here. And then use this initial model to answer parts B, C, and D. Part B, by taking moments about A, show that S equal to 1/2 mg cos theta. Okay, so they want us to take moments about point A. So because those two forces are on the same line as point A, so the moments for those two will be equal to 0. So you can just ignore those two. Yeah. So we only need to worry about mg and S. So mg is in the clockwise direction and S is anti-clockwise direction. So to set them up, because it's in Newton equilibrium, clockwise moments is equal to anti-clockwise moments. So we just do mg times by its shorter distance. So from point A to mg, the shorter distance will be this length. And then we know it's a uniform rod. So that means this length is only half of the whole length 2A. So that would be just A. So therefore that length is A cos theta because that's adjacent. Yeah. And then that's equal to S times by the shorter distance. So for the moments, we always use the force times by the shorter distance from the point we try to take the moments on. And then like you use the whole line. So point A to the line where the force lies on is this distance, which should be the same as this one. Yeah. And then that's the opposite of the angle. And the whole length here is 2A. So it has to be 2A sine theta. And now we just have to rearrange them. Divide by A for both sides, A will cancel out. Divide by 2 for both sides, we will half times by mg. And then divide by sine for both sides, sine over cos give us, cos over sine things we divide by sine for both sides. Then cos over sine is just cot. So S is just equal to half mg cot theta. That's all. And then for part C, the coefficient of friction between the rod and the ground is mu. And then given that tan theta equal to 3/4, find the value of mu. Let me clean this a bit. So for the forces, we have only 4 forces here. One is R, another one mu R, the friction, and mg the weight, and S the normal reaction at B. So because it's limit in equilibrium, so that means up equal to down, R equal to mg, and then left equal to right. So mu R has to be equal to S. So we can now just substitute one to the other. So we know what R equal to. So R is equal to mg. And then we know S, what's S equal to? That's just half mg cot theta. So then divide by mg for both sides. So mu is just equal to half times by cot theta. And then we know tan theta equal to 3/4. So cot theta has to be 1/10, which is 4/3. So half times by 4/3 is 2/3. That would be the value of mu. And then part D, find in terms of M and G the magnitude of the resultant force acting on the rod at A. So there are 2 forces act at point A. One is a normal reaction, another one is a friction. Yeah. So what this question means, they want us to find the resultant force acting on the rod at A. So basically, they just want us to find the resultant force of those two. So one is to the right-hand side, which is mu R. We know mu is 2/3. And we know R is mg, so that would be 2/3 mg. And then for the vertical direction, R is just equal to mg. So we just have to do Pythagoras to find the magnitude of the resultant force. So because they are in terms of mg, we can just leave mg out. So just mg times by the square root of 1 square, because mg means 1 mg. So 1 square plus 2/3 square. So put in the calculator, that'll be root 1 square is 1 plus 2/3 square, which is root 13/3 mg. So that'll be the answer for part D. And then next part, in a new model, the rod is modeled as being non-uniform, with its center of mass closer to B than it is to A. So basically, the center of mass is more like to this side now. And then state whether this new value for S is larger, smaller, or equal to the value that S would take using the initial model. So clearly, S would be bigger than before, because when we do the moments about point A, moments is force times by the shortest distance. So from point A to mg, the previous mg, this is the shorter distance, but now it's moved more towards B, so it's longer than before. So that means the moments for mg about point A is bigger. So therefore S has to be bigger, because like the equation we set it up for S is mg times by A cos theta equal to S times by 2A sine theta. That's how we set the equation to work out S. So now we know this A is getting bigger. So like it's not A anymore, it's something bigger than that. So that's why when you work out S, when you rearrange them, so mg times by A cos theta divided by 2A sine theta. So the denominator doesn't change. And if the numerator, this values get bigger, the numerator is getting bigger. So S will get bigger. So to answer this question, you just have to say the new value for S is larger than the initial model as the center of mass closer to B will make the moments of the weight about point A larger.
Thank you for watching the video. If you have any questions, you can leave some comment. And then if you find the video helpful, please like it and subscribe it. May the A star be with you.